Thank you very much, President Tripathi. It's my pleasure to introduce our guest speaker today. Connie Brinkerhoff is the Nathan Smith Professor of Molecular Medicine and Biochemistry, as well as being Associate Dean of Science at the Dartmouth Medical School. In addition, she's a distinguished alumnus of the University of Buffalo School of Medicine, where she received her PhD in microbiology. Dr. Brinkerhoff's formal scientific career began with an interest in autoimmunity, which she pursued during her PhD studies. But shortly after joining the faculty at Dartmouth, she began investigating a group of enzymes known as the matrix metalloproteases, which digest extracellular matrix and are important in remodeling of connective tissue. These enzymes, in addition, have a dark side, being involved in the degeneration of connective tissue during arthritis and in mediating tumor metastases. As such, understanding how these enzymes are regulated is a very important issue in human health. Dr. Brinkerhoff received her BA in biology at Smith College before coming to UB for graduate studies and joined the faculty at Dartmouth as an instructor, then rapidly rose through the ranks, becoming a full professor by the late 80s. Her research has been continuously funded by the National Institutes of Health for over 30 years, including holding a prestigious merit award from the National Institute of Arthritis and Musculoskeletal Disorders. Her research is currently in two related projects involving matrix metalloproteases, one which examines their genetic and epigenetic regulation, and the other examining their role in metastatic phenotype of melanomas. She and her colleagues have published over 140 papers in these areas over the course of an illustrious career. I would say that in addition to her outstanding credentials as a research scientist, Dr. Brinkerhoff has also made many important administrative contributions at Dartmouth, including serving as the acting chair of the Department of Biochemistry and as acting provost of the college. And she has held two named professorships there. Prior to becoming the Nathan Smith Professor, she was also the Oscar Cohn Distinguished Professor of Molecular Medicine. Dr. Brinkerhoff's most recent work has yielded important new insights into the connection between inflammation and matrix metalloprotease production, as well as helping to elaborate the role of this class of enzymes in cancer metastasis. Inhibitors of these enzymes have great potential for therapeutic roles in both arthritis and cancer. Dr. Brinkerhoff is a strong believer in the philosophy that only by understanding the basic biology of a system can effective new treatments be discovered and refined. It is a pleasure for me to welcome her back to the University of Buffalo School of Medicine and Biomedical Sciences.
See if that works. Thank you, Dean Blumenthal, President Tripathi, Dean Kane, faculty, graduating students, family members, and guests. It is an honor and a pleasure to be with you. Today, I'm going to speak about 200 years of science and medicine. My father was born 100 years ago in June 1911. As a toddler, he contracted diphtheria. The disease is caused by bacteria and the toxins they produce. The toxins destroy healthy cells, usually in the throat, and the dead cells form a gray or gray-green membrane, which can cause suffocation. Apparently, my grandmother physically destroyed the membrane, presumably helping my father to breathe. A life-saving antitoxin had been developed around in the late 1800s, and it was in wide use by the 1910, so my father likely received it. How common was diphtheria back then? Well, in Boston, where he lived, in the early 1900s, there were 144 cases in just 1 week. This is compared to 3 cases in the entire U.S. between 2001 and 2007. In 1900, the Boston Medical and Surgical Journal reported that, quote, if the local process of membrane formation can be stopped, the life of the patient will be saved. The membrane could be torn off, leaving a raw surface, but the organism of diphtheria would not be destroyed and the membrane would reform. No germicide could be of sufficient strength to effectively destroy the bacteria without causing destruction of the mucous membrane and thus opening a fresh field for growth of the organism, end quote. How primitive this sounds. With the advent of the antitoxin, one physician wrote, the treatment is simple. 10 cubic centimeters of the serum are injected into the skin. The temperature in nearly every case begins to descend in from 8 to 20 hours. The membrane softens and in many cases comes away in shreds. No other medicines are given except to weak patients who are supplied with an abundance of wine, milk, and beef tea, end quote. How did we go from scraping away a gray-green suffocating membrane to the benign process of administering an antitoxin? In a word, classic basic science, observation and experimentation, and the combined knowledge of several scientists. In 1884, Frederick Loeffler isolated the causative bacterium, and in the 1890s, Emil von Behring in one laboratory and Emile Roux, along with Alexander Yersin in another lab, demonstrated, in fact, that it was the toxin that caused the disease. Subsequently, both groups developed the antitoxin, and both vied and competed for the first Nobel Prize in Medicine in 1901. Eventually, amid the controversy, it was awarded to von Behring. No matter to whom it was awarded, it serves as a testament to the devastation wreaked by this disease. Now let's fast forward to the 1930s. My father, having survived diphtheria, is now an intern resident in medicine at Boston City Hospital, where many patients had tuberculosis, TB, also known as consumption or the Great White Plague. In 1936, 1 in 20 deaths was due to tuberculosis, making it the most deadly of contagious diseases. Treatment was a sanatorium where rest and good nutrition offered the best chance of allowing the patient's immune system to wall off the infection in the lung. Thankfully, my father never got the disease, but neither did he forget what he saw in those wards. Years later, in the 1980s, young docs at the famed Massachusetts General Hospital struggled and scratched their heads, trying to diagnose strange symptoms in an 8-year-old girl. My father examined her, asked a few pertinent questions about the household, and concluded that the girl was afflicted with TB, infected by a nanny who had come from Jamaica, where the disease still exists. The message is clear. Do not forget what you have learned in all your experiences. They can come back to haunt you and to help you. Of course, in the Western world of today, both diphtheria and TB are readily cured by antibiotics, and most patients are in fact cured. We take these cures for granted, and the infectious diseases of the early 1900s are simply dismissed as non-events of today. Now it is my turn to enter the picture. It is the early 1950s, and I am a young girl away at summer camp. The scourge is polio, a word that invokes instant terror and images of iron lungs, paralysis, wasted limbs, wheelchairs, and crutches. Polio is a contagious disease, not caused by a bacterium, but by a virus. It attacks the nerve cells of the brain and spinal cord and can cause paralysis. Polio was very common, and no one was immune, not even the future President of the United States, Franklin Delano Roosevelt. In August of 1921, he was only 39 years old. At first, he felt only mildly ill, but soon he had a raging fever. His legs ached, and he could not move them. The future president had contracted polio, which left him paralyzed from the waist down for the rest of his life. That was in 1921, and by the 1950s, the polio epidemic was in full swing. At its height in 1952, 60,000 cases were reported, and over 3,000 people died in the United States alone. No wonder people were terrified. For those of us at camp in Maine, when polio was in the air, overnight hiking trips to the White Mountains were canceled, and counselors were quarantined at camp, no trips to town. Then in 1955, the Salk vaccine was shown to prevent the disease. It was a miracle. Later, the Sabin oral vaccine was developed, and today polio has essentially disappeared from developed countries. So far, I have highlighted 3 grisly diseases of epidemic proportions, each of which touched my family directly. Today, they are history, thanks to the unrelenting curiosity and hard work of many scientists dedicated to finding the causes and developing effective therapies, the antibiotics that kill bacteria, and the viruses that amplify our immune responses. Within the past 50 years, the end of the 20th century, the focus has turned to molecular biology, DNA, RNA, and protein. In the beginning, progress was slow. A critical step was elucidating the genetic code, and the contribution of the biophysicist Dr. Rosalind Franklin was indispensable. She used X-ray diffraction to show a pattern of atoms, and based on her images, in 1953, Watson and Crick revealed the structure of DNA. For their discovery, they shared the Nobel Prize in 1962. It was reported, however, that Dr. Franklin experienced difficulties as a scientist because she was a woman. Nevertheless, she exceeded in doing what she wanted, and that is the critical point. She was dedicated to her work. She found personal satisfaction and her own joy in what she did every day. Dr. Franklin's career provides an important lesson: being passionate about your work and true to your own values and your sense of integrity. Nonetheless, I would be remiss if I did not address unique issues to women in science. A National Science Foundation survey of earned doctorates revealed an increase from 18% of women getting doctorates in 1973 to 41% in 2005. Comparably, males dropped from 78% in 1973 to 41% in 2005. Thus, the gender gap in degrees awarded seems to be closing. Importantly, some of these gains are reflected in the number of women with tenure-track faculty positions and full professor status in the sciences. However, there are still disparities in terms of their success in climbing the academic ladder. The challenges of juggling marriage and child-rearing remain. Now I would like to say a few words about my own journey through science. After graduating from college, I was married within 2 weeks to someone I had met at that summer camp. We lived in New York City, where I worked as a tech at Rockefeller University. I was bored, often finishing the work assigned to me in early order and leaving the lab. I did that once too often, and I was summarily fired one day. Shortly thereafter, we moved to Buffalo, found a small apartment in Eggersville, and began graduate school. My husband was studying for the PhD in philosophy, and I in microbiology and immunology. Life was terrific. I loved the lectures, loved the lab rotations, and was thrilled to be accepted into Dr. Knowles Rose's lab for my PhD thesis. Dr. Rose, by the way, now in his 80s, is still doing science at Johns Hopkins. However, unexpectedly, I became pregnant, not once, but twice. The 2 children were 16 months apart, and one faculty told me, quote, "You have my respect, but not my sympathy," end quote. In other words, this was my issue, and it was up to me to deal with it. Dr. Rose was understanding and patient, but I had to get the work done, and I defended my PhD thesis 9 months pregnant with our second child. A few years later, I became a postdoctoral fellow at Dartmouth, and as you know, I have remained there ever since. So now it is 2011, and stop for a moment and reflect on the medical and social progress of the last 20 to 30 years. Who could deny that we live in an age of medical miracles, many of which are based on the explosion in molecular biology that has occurred during this time? We have made enormous strides against cancer. Many individuals are alive and well, either cured or living with cancers that would have killed them quickly of only a few decades ago. Numerous biologic therapies, such as those directed at neutralizing inflammatory mediators, are alleviating the pain associated with autoimmune diseases. Advances in bioengineering have made joint replacements common events, restoring vigorous activity to others who might otherwise be confined to wheelchairs or crutches. Incredible imaging techniques predict the need for cardiac surgery before the onset of a lethal event, thus saving lives and preserving the quality of life. These are huge advances, each building on the incremental and scientific achievements of individual scientists and engineers. But we are not finished. Success is not complete. Bacteria continue to evolve with lightning speed to circumvent current antibiotics. Cancer cells continue to mutate and outsmart even the newest therapies. The miraculous anti-inflammatory biologic agents that dampen the pathways that give rise to autoimmune diseases also oppress the immune system and make its recipients at greater risk for cancer and infection. Joint replacements can fail and, as a result, actually increase pain and disability. Where will we be 100 years from now in 2111? A recent publication from Case Western Reserve predicts that almost every child born in the Western world a century from now will, quote, be cataloged right away by sequencing Junior's genome in search of warning flags. The article further predicts that in adulthood, open heart surgery won't be in the cards. Cracking open people's chests will be considered crude. Instead, within 100 years, researchers expect to generate tissues made from a person's own DNA without taking someone else's heart or kidneys, as we do today. Other scientists in this group predict restoring spinal cord function with artificial nervous system circuits powered by electrical signals. These pie-in-the-sky predictions may inspire shock and awe, and perhaps they will even come true. So what does the future hold? The current buzz is translational medicine, from the bench to the bedside. While sounding simple, in reality this is very difficult. Not only is it technically challenging to take an exciting conceptual advance first seen in yeast or even in mice to practical and successful testing in men, it might flop since yeast and mice are far removed from man. Thus, the reality of translating enormously important advances into successful and feasible protocols remains elusive. It almost feels like being back 100 years ago to the initial discovery of bacteria and how they cause disease. It was a puzzle whose solution now seems amazingly simple with a hindsight of 2020. Will the face of science 100 years from now resemble the predictions of the scientists at Case Western Reserve? Most likely, we will all not be here to witness that. But you will be able to influence how we get there. Each of you who is graduating today does not need to aspire to be a Nobel laureate or a PI running his or her own lab. As science and society converge ever more, the need for well-trained scientists such as yourselves to engage in all aspects of society, the scientific, legal, educational, journalistic, and entrepreneurial becomes even more acute. There are multiple ways to use your scientific training and your talents to express your excitement and your enthusiasm. What will you do? How will you help us get to the next 100 years? Congratulations and best wishes to you all.